Okay, this is Chemistry Chapter 12, Lecture 2. Our material starts on page 395 in your book. And on your notes, we are at Dalton's Law of Partial Pressures, and that is in the middle of page 3. All right, so Dalton's Law of Partial Pressures, pretty simple concept. Of course, Chapter 12, we're just talking about gases in Chapter 12. And if you have a container of gases, let's say in our particular example we have some CO2, some O2, some nitrogen. If you have a container of gases, the total pressure in that container, you find that just by adding up the pressures of the individual gases. So in this container, the total pressure, we would add up the pressure of the CO2 plus the pressure of the O2 plus the pressure of the nitrogen, and we would get the total pressure in the container. Now the next concept on your notes is called vapor pressure. So I've got a good video linked in the description box, so please watch that about vapor pressure. But if you were to have, let's say, we've got a beaker, and we've got some water in that beaker. And of course, you've got water molecules all throughout that liquid. What's going to happen over time is some of those water molecules are going to hit the surface, and escape. And they're going to escape and form a little vapor cloud, all right, above the surface of the liquid. Vapor pressure is the pressure of the gas that sits above the liquid. Okay, so a really good video that I've put in the description box. Just make sure you watch that. It's much better than my little drawing here. All right, might have been easier if I had drawn the cloud up above the beaker. You could see a little better, but that's the cloud of vapor. Now you can't necessarily see it. Okay, but that cloud of vapor has a pressure, and that's what we call vapor pressure. All right, boiling point is the next thing on in your notes, and that's the temperature at which the vapor pressure is equal to atmospheric pressure. You can actually boil a liquid, let's say in this case water, and it doesn't have to be hot. As long as you reduce the pressure above the beaker, the pressure of the air above the beaker, then that'll make molecules be able to escape easier. All right, and so you can boil at room temperature. So it doesn't really have anything to do with temperature. It has to do with the atmospheric pressure, the boiling point. So I'm going to show you a video of boiling water at room temperature. All right, and then we have collecting gas over water. All right, so we have a table in the book that you're going to be needing to refer to for the homework and for these on your own problems. The vapor pressure of water at different temperatures. Okay, so you can see that cloud of vapor that sits above the liquid has a pressure at 23 degrees of 21.1 torr. At 60 degrees, 194.4 torr. Okay, so we'll be using this table. All right, don't have to memorize any of that. All right, let's look at on your own 12.4. Turn over to page 399. All right, that one says a chemist collects carbon dioxide over water. That means we're going to use the table I just showed you. Okay, over water means water vapors mixed in. The pressure of the gas in the collection container was 961 torr. If the temperature was 22 degrees C, what's the pressure of the carbon dioxide? Okay, so from Dalton's law of partial pressure, we know that the total pressure is going to equal to the pressure of the gases. Well, those gases are CO2, and since we collected it over water, H2O. Well, it said that the total pressure is 961 torr. We don't know the pressure of the CO2. I'm going to call that X. And then we can get the pressure of the water because we know the temperature. At 22 degrees, the pressure of the water is 19.8 torr. All right, so solving for X, we'll have 961 minus 19.8. So that would be 941.2 torr. All right, so that's all there is to it for that problem. All right, turn the page and we'll talk about mole fraction. All right, so this still has to do with the pressure on gases in a container. So mole fraction, if I'm going to figure out the mole fraction of, let's say, gas 1, we'll call that X1. We use X to denote mole fraction. It's the moles of gas 1, so this is for, it could be gas 2, gas 3, whatever the gas is, over the total moles in the mixture. All right, so that's the mole fraction. We're going to need to calculate mole fraction to figure out the pressure on each gas. Now, somewhere on your notes, all right, up near this mole fraction section, you need to write this. This is something that that I didn't type into the notes, but the pressure of an ideal gas, this is very important, does not depend on the identity of the gas, only on the quantity. So I don't care if it's CO2, if it's oxygen, if it's nitrogen. It's only about how many moles you have. The number of moles determines pressure, not the identity of the gas. All right, so let's look at 12.6. Oh, by the way, well, I'll erase. Let me erase this, and then I'll put the next equation up. All right, so we're going to refer back to your mole fraction equation, and let's do 12.5. And we are on page 400. Look at us go. So it says a tank of compressed air contains 672 grams of oxygen, 2,184 grams of nitrogen, 40 grams of argon. What's the mole fraction of each component in this mixture? Well, we're going to have to get moles. All right, so for oxygen, O2, we've got 672 grams. Need to change that to moles. O2 would be 32 grams. All right, so that is 21 moles. Right, the next component, next gas is nitrogen. It says we have 2,184 grams. All right, we're going to change that to moles. Nitrogen N2 is 28 grams. And that's going to be 78 moles. And then for argon, problem says we have 40 grams. Right, argon weighs 39.9 grams if you look at your periodic table, 39.9 grams per mole. Well, that's going to be 1 mole. we need to add up the total moles in the mixture. So it's 21 plus 78 plus 1. That's going to be 100 moles. So the mole fraction of each component, so we call that X for oxygen. You take 21, the moles of the individual gas, divided by the total, 100, and that's 0.21. The mole fraction for N2, you take the number of moles of N2 divided by the total moles, and that's 0.78. And then for argon, 1 mole divided by the total 100, that's 0.01. So the mole fraction should add up if you want to check to 1. All right, might be a little off due to rounding, but something really close to 1, 0.99, 1.01, something like that. All right, so that's how you get the mole fraction. So these would be your answers. Now we can use that to help us find the pressure on each gas. All right, so I'm going to erase this, so pause if you need to. All right, so the equation that we're going to use to find the pressure on each individual gas, so let's say it's gas 1, pressure 1. What you do is you take the mole fraction of that gas times the total pressure in the mixture. All right, let's take a look at 12.6, and this is going to be on page 402. All right, 12.6 says a sample of artificially made air contains 78 grams of nitrogen, 21 grams of oxygen. If the pressure of the air sample is 760 torr, what's the partial pressure of each gas? So the total pressure is 760. What's the partial pressure on each gas? Well, we're going to have to figure out the mole fraction first, because mole fraction is part of the equation. So for nitrogen, says we have 78 grams. Need to change that to moles. Nitrogen weighs 28 grams per mole. So 78 divided by 28 is going to be 2.79 moles. Oxygen, says in our problem that we have 21 grams. Need to change that to moles. All right, so 21 over 32 would be 0.656. All right, we're going to total that up. 2.79 plus 0.656 would be 3.45 moles. So the mole fraction for N2, we're going to take the 2.79 divided by the total, 3.45, and that is 0.81. I'm going to use that in a second. The mole fraction for O2, you take the 0.656 divided by the total moles, 3.45. That's going to be 0.19. We can check that. That looks right because that adds up to 1.0. Now let's get the pressure on N2. So we're going to use this equation. It's the mole fraction, 0.81, times the total pressure, which the problem said was 760 torr. All right, so that is 615.6. And then the pressure on O2, we take that mole fraction, 0.19, times the total pressure, 760. that gives us 144.4 torr. Now, what should those two add up to? Well, they should add up to the total pressure. You can check that, but that's 760 torr. Right, so the answer to this question, what it's asking, would be right there, the pressure of N2 and O2. But it's a pretty long problem because we had to figure out the mole fraction first. And then you can check your mole fraction. Does it add to 1? Check your total pressure. Do the individual pressures add up to the total pressure? All right, one more problem, and that will finish up this lecture. Pause if you need to. So let's take a look at 12.7. This is a shorter problem. And this is on page 402. All right, that one says a chemist produces hydrogen gas in a chemical reaction, collects it over water, so we're going to use that table, at 23 degrees C. If the pressure of the gas inside the collection vessel is 781 torr, what is the mole fraction of the hydrogen gas in the vessel? Okay, so first of all, let's look back and get the vapor pressure of the water. All right, at 23 degrees C, so we flip back to table 12.1. We see that's 21.1 torr. All right, so we'll come back to that. All right, we know that the total pressure, according to Dalton's law of partial pressures, is going to be the pressure of the hydrogen plus the pressure of the water. All right, we just looked at the table to see that the pressure of the water is 21.1 torr. That's at 23 degrees. The total pressure, the problem says, is 781 torr. There you go. There you go. And that equals the pressure of the H2. What's that? So the pressure of the H2 is going to be 781 minus 21.1. That's 759.9 torr. Now that's not what it asked. What it asked is, what's the mole fraction? Well, we can get the mole fraction by rearranging this equation. The mole fraction of our gas, H2, is going to be the pressure of H2, okay, in this case that's pressure of 1, divided by the total pressure. Right, the pressure of H2 we figured was 759.9. The total pressure is 781. So mole fraction doesn't have a unit, so that's going to be 0.97. That means that 97% of the gas molecules are hydrogen in this mixture. All right, that does it for lecture 2. The homework from this section that you are capable of doing, you can do review questions, page 415. You can go ahead and finish those up, 8 through 10. Practice problems, page 416. You can do 4 through 7. All right, so that does it for lecture 2, and I will talk to you next video.